Hey A&Pers, this is Dr. Jones checking in. This is A&P 2, lecture test 5, video 7, and we're starting at the top of page 13. I am happy to see you all back, so let's dig in. We're going to review this from the bottom of page 12 before we move on because these concepts are what we're talking about today. So hydrostatic pressure is fluid pressure. It's the pressure of the fluid moving. Osmotic pressure is the force with which water diffuses into a solution with a higher solute concentration. If you recall this picture from 2401, the osmotic pressure is the force of the water moving through the holes. And colloid osmotic pressure is a pressure due to the materials, the proteins in solution. So it's the force of the water moving due to these solute molecules, usually proteins. In this case, proteins. And as I mentioned at the end of the last video, a colloid is a solution with large organic molecules in suspension. So now we're on page 13 and our chart. And I'm going to move me out of the way. Okay, so first we have, we need a pen. What color pen should we do? I think red will show nicely. There we go. So the glomerular hydrostatic pressure is the blood pressure in the glomerulus. So the hydrostatic pressure is the fluid pressure, and the fluid here is the blood. And it moves fluid from the glomerulus into the capsular space at an average of 50 millimeters of mercury, and that is this arrow right here going that direction. So we can do the capsular in let's see, what color is it on here? Yellow? We have a yellow. It's probably an evil neon. Oh, it is. There we go. So here's our capsular hydrostatic pressure, which is the fluid already in the capsular space. And so it pushes back from the capsular space back into the glomerulus at roughly 15 millimeters mercury. And then we find the difference. And when I say the difference, I'm talking about subtraction. So right here, that minus sign, that's the difference. The difference is when you subtract. What difference is what you get when you subtract. Okay, so the net hydrostatic pressure is the glomerular hydrostatic pressure minus the capsular hydrostatic pressure. As you recall, 50 moving this way minus 15 moving back, and that gives us a 35 average millimeters mercury net hydrostatic pressure. Let's see what that says. The difference between glomerular hydrostatic pressure and capsular hydrostatic pressure is net hydrostatic pressure. Yeah, I just said that. Thanks. Next slide. Okay, I can't find the arrows, so use the arrow on that didn't work. Use the arrows on the keyboard. Okay, so we talked about colloid osmotic pressure, and here you go. Here is, we're back to blood, so we'll do red again. Red is fun. Red. The blood colloid osmotic pressure is the osmotic pressure in the glomerular capillaries, and so that's the force of the osmosis, and it's moving backwards. So from the glomerulus, from the capsular space to the glomerulus at roughly 25 millimeters mercury. And then the net filtration pressure, we have a brown. We need a brown. I don't think the gray would show. We did black. We haven't done green lately. There we go. And net filtration pressure is the net hydrostatic pressure minus the blood colloid osmotic pressure. So it's everything. 50 minus 25 minus 15 is on average 10. A positive 10. And if it's a positive number, then you make filtrate. You squeeze fluid out of the glomerulus, the blood vessels, into the capsular space, and the fluid in the capsular space is filtrate. Okay. And we'll talk about what happens if that quits here in a second when we get to it in the note set. So you may see this with the net hydrostatic pressure written out. So you may see this as the glomerular hydrostatic pressure minus the capsular hydrostatic pressure. in parentheses, minus the blood colloid osmotic pressure. And don't let that freak you out, because the net hydrostatic pressure is the GHP minus the CSHP. It's actually easier to say the words than the abbreviations. That's weird. Okay, so either way they write this out, it's the same thing. Okay, so don't let that worry you. Oh, now there's arrows. Excellent. So a positive net filtration pressure means that fluid is forced from the glomerulus, this is the net filtration pressure here, net filtration pressure, into the capsular space. Why can we disregard capsular colloid osmotic pressure in healthy kidneys? Because in healthy kidneys, there aren't any proteins here. The filtrate, if the filtration membrane is working correctly, the filtrate should not include any proteins, or just small amounts of albumins, but not enough to create the capsular colloid osmotic pressure. I had to look at it, make sure I had it right in my head before I said it. I had it right. And what about the afferent efferent arterioles contributes to high GHP? I've mentioned this. The efferent arterioles have a smaller diameter than the afferent arterioles, which jacks up the pressure inside the glomerulus, forcing fluids out through the filtration slits, through the filtration membrane. If blood pressure went up, how would the filtration pressures change? If you increase the blood pressure, you would increase this glomerular hydrostatic pressure, which would increase the net hydrostatic pressure, which would increase the net filtration pressure. So increase. And if blood pressure dropped, then you would drop the glomerular hydrostatic pressure, which would drop the net hydrostatic pressure, which would drop the net filtration pressure. And if net filtration pressure goes lower than 0, then no filtrate is being formed, and you just entered kidney failure. Luckily, we have a few ways to try and avoid that, which we'll talk about. The glomerular filtration rate, here we go, is the amount of filtrate produced per minute. It is about 125 liters a minute, and 10% of the renal artery output becomes filtrate. In the course of a single day, you make 180 liters. You don't have 180 liters, but you make 180 liters of filtrate. So it gets filtered, your entirety of your liquids get filtered numerous times a day. And 99% of that 180 liters is, of course, reabsorbed. 180 liters is 48 gallons. And that is 70 times your total plasma volume. So the GFR and blood pressure. The blood pressure drops. When blood pressure drops 20% to 40 millimeters mercury, the net filtration pressure drops to 0 millimeters mercury, and you're in acute renal failure. However, first, what can cause acute renal failure? Blood loss, shock, and dehydration. That's page 13. Flip. Filtration depends on blood flow to the glomerulus to maintain normal filtration pressures. Let me move me back up. There we go. Stay out of the way. Autoregulation, here we are. Maintains GFR when the blood pressure changes. So how do you not go into acute renal failure every time your blood pressure drops? The diameters of the afferent and efferent arterioles and even the glomerulus change to maintain a positive GFR, a positive glomerular filtration rate. The release of renin, this is R-E-N-I-N renin, not R-E-N-N-I-N renin, which you know is a digestive enzyme used to curdle milk and make cheese. This is the renin-angiotensin-aldosterone system, the RAAS that we're talking about. And it ultimately restricts water and salt loss in the urine by stimulating reabsorption by the nephron, and when we get there we will talk about how that happens. 3 triggers that cause the juxtaglomerular complex to start the renin-angiotensin pathway. Number 1, decrease in blood pressure at the glomerulus. 2, sympathetic stimulation at the juxtaglomerular cells. And 3, a decrease in the osmotic concentration at the macula densa and the DCT, which you know all these terms from the lab material, right? If not, please go learn. Need to know. The renin-angiotensin pathway increases blood volume. I wrote this part of the note set before. It's now the renin-angiotensin-aldosterone pathway. So it increases blood volume, increases blood pressure, which increases the GHP, which increases the NFP, which increases the GFR. So that's 2 lines of increase. Sympathetic activation vasoconstricts the afferent arterioles, the ones going in, which decreases the GFR. And this slows the production of filtrate. It overrides local regulations to save fluid, which makes sense for sympathetic because if you're running for your life, now is not the time to spend a lot of energy filtering things. How can heat and strenuous activity impact the kidneys? Less than 25% of normal renal blood flow. So it lowers renal blood flow, which lowers filtrate production, which increases waste buildup. I had that written down. Okay, and hematuria is blood in the urine. 18% of marathon runners have blood in their urine after running a marathon. So running exercise is good for you up to like a point, and marathoning is a little bit above that point. Again, informed consent, it makes you happy and you know that it's not actually good for you, but it's what you want to do, then you do it. It's your body, it's your choice. But do it, make that choice informed. Informed consent, make the choice knowing that it's a tiny bit past what's actually healthy for you. And do what makes you happy, but do it knowing the truth. Truth hurts. Lies hurt more. Okay. There we go. The renal tubules. All right. The renal tubule has 3 specific functions. 1, reabsorb organic nutrients. 2, reabsorbs more than 90% of the water. And 3, secretes wastes. As filtrate passes through the renal tubules, about 99% of it is reabsorbed. There are 3 parts of the renal tubule, as you know from the lab material: the proximal convoluted tubule, the nephron loop, and the distal convoluted tubule. These are the 3 parts of the renal tubules, and they all work on these 3. But as we'll find, which is probably in the next page of the note set, so I'm probably getting ahead of myself, but you need to know, the proximal convoluted tubule does the bulk of the reabsorption. It reabsorbs a bunch of nutrients and also the water. And when I say reabsorb, once the fluid has been squished into the capsular space and it is now filtrate, that fluid is no longer quite considered part of you because it's no longer in your cells. It's in a tubular system that leads to the outside. So the parts that are in the fluid that you need, like 99% of the water that's going to get reabsorbed, and the nutrients, the glucose, the ions that you need that are going to get reabsorbed, these cells that make up these renal tubules are going to pull those ions and glucose out of the tubular fluid and put them into the peritubular space. And not peri the platypus, but peri, P-E-R-I, which means around. The peritubular fluid is the fluid around the tubules. Tubular fluid is, of course, the fluid in the tubules. And then the things that are reabsorbed go through these cells into the peritubular fluid and then will enter the peritubular capillaries. In the cortex, the peritubular capillaries will be the... Well, I came here and now I can't remember the word. Are they peritubular capillaries? Yeah. And then in the medulla, it's the vasa recta. That was the other one. So when we say reabsorb, we're meaning taking back into the body, which means they're not going to get peed out. And then when we say secrete waste, that's going the other direction. So there are wastes that are in the bloodstream, in these peritubular capillaries that are around the tubules. And those wastes are going to be go through the cells are going to take them and enter them into the tubular fluid in the renal tubule so that they get peed out. So these are things that are too big to go through the filtration membrane, but they need to be filtered out. And so that is secreted wastes. They get secreted, moved into the tubular fluid so that they will be peed out. Okay. Basic concepts. And that was page 14. And how long have I been talking? Oh, I didn't start the timer. That one doesn't have a timer. When you do the audio recording in this setup, there's a timer. Okay, well, I'm going to call it because that was 2 pages. So we did page 13 and page 14. So thank you as always for tuning in. This has been ANP2 Lecture Test 5 Video 7 covering note set pages 13 and 14. The education must go on. Dr. J out.